As introductions, my name's Avi, Jayant and Kailiang, and we're engineers on the Android camera team, which is not the camera app team, but the team that develops the camera framework on the OS itself. So maybe not quite the crowd that we generally talk to, so this is nice to have a more application-focused crowd. Today we wanted to talk about what... There's a slight bit of echo, by the way. Thank you. We want to talk about what we've been calling math and modeling for camera developers. And the best way to start would be to start with the question of, how does a sample like these work, right? And I don't mean what libraries can you call and what APIs can you use to create something like this. I mean more along the lines of, can you write those libraries? Can we figure out the math that goes behind creating an experience like this? And so the goal of today's talk is to give you an idea of what some of the math looks like. And just as a heads up, this talk is going to be slightly math heavy. And I understand this is right after lunch, so some of you might be sleepy. Don't get hung up on the details. We were giving this dry run, and one of our coworkers who has a PhD, he's like, OK, I need to get my pen and paper out because I need to sit with all of this math and digest all of this, right? So take it at your own pace. Just don't get lost in the details. We'll try and highlight the major parts that you need to understand to immediately move forward. But the goal of this is for you to get an insight into it and hopefully to dive deeper as you see fit. Just as prerequisites, not actual prerequisites, we won't kick anyone out, is if you understand some basic linear algebra, matrix math, that'll be really helpful. If not, just think of it as like slightly more convoluted operations than you usually deal with. If you have some camera experience, that's good because this is all camera-based, so that's helpful context. And if you have graphics experience, you may not need this talk, to be perfectly honest. A lot of what we're talking might look very familiar to what you already know. So today we're talking about three things. Well, two things in a little bit. Camera intrinsics is what we use to take the word and make a picture. So it's the thing that the camera does using physics, right? How do we show that as mathematics? Camera extrinsics is, it's not the official name, but it's the reverse operation. How do you take image or images and convert that into a three-dimensional word? And then finally, because we're all Android developers, well, most of us anyway, what APIs do we have to create something like that? So let's start with camera intrinsics, and then I'll later hand over to my colleagues for the rest of it. So if you think of a camera, it's basically a box that takes a three-dimensional word and gives you a two-dimensional picture, right? So I don't know if it came out of cameras or not, but mathematicians have a name for it called projection. It's very appropriate. I asked Wikipedia what it means, and the definition it came up with, in mathematics, a projection is an idempotent mapping of a set into a subset. All this means is it takes a set, which is three-dimension, and converts it into a subset, which is two dimensions. Idempotent is doing some heavy lifting, but we don't need to care about it for cameras. If you start looking up three-dimensional projections, you'll come up with two big types of projections. One is called perspective, and this is popular because that's what our eyeballs do. And the other is orthographic, and that's popular because that's what engineers do. The main difference is, for orthographic projection, parallel lines stay parallel. Things that are near or far don't affect in size, so relative sizes stay the same. And perspective projection is what we're intuitively familiar with. Things that are close look bigger, things that are further out or smaller. All parallel lines meet at some vanishing point at infinity. But I do want to point out that they aren't as different as it seems. Orthographic projection is somewhat of a limiting case of a perspective projection. So if you're looking at the moon, that might as well be an orthographic projection of the moon. It's sufficiently far enough away. So let's dive into the math, but without the math. So the goal here is, if we have a word, can we come up with a mathematical operation that makes it an image? And 3 dimensions is difficult, so let's reduce it down to 2 dimensions. We have an object, a big logo, and we have a regulation 2-dimensional camera. with a one-dimensional sensor. And to simplify things, this is a pinhole camera. I'm sure people are familiar with what a pinhole camera is. It's just a camera that looks through a small little pinhole, if you will, and lets a very limited amount of light in, right? And the goal here is to see if we can come up with an intuitive idea of how a camera captures an image, or the image is created, if you will. So the first thing you might think of doing, or maybe not, is to draw what's called a principal axis. And the special thing about this axis is, oh yeah, I have a pointer, by the way. So track the pointer. I'll try and point out stuff that's important. The special thing about this axis is that it passes through the pinhole, and it's perpendicular to the sensor. And we call it the principal axis. We'll get to why in a bit. It does not need to pass through the outside word. There's no reason that it passes through G. It just happens to be nice for the diagram. So let's start drawing light rays, right? Light rays mostly travel in straight lines. We won't get into the physics behind it. But a light ray coming out of the object has to pass through the pinhole and touch the sensor for it to become an image, right? So just using these ideas, we can start drawing lines. And in this example, we'll be going top to bottom. So the first line that you might think of would be tangent to this curve around here, and it'll project its image down here, right? Oh, I accidentally clicked. But so scanning down, it keeps going down. All of these rays coming out would create a red image on the sensor here, right? So far, so good, I hope. We do the same thing, and now we find that the yellow bit's been projected. And just to complete the image, we go even further down until it's tangent to the curve down here again, and that's all the green bits, right? So two things to notice here is, to us, from 3 dimensions, this red length, the yellow length, and the green length, these look about the same. But to the image here, the yellow length dominates both green and red. And that's perspective projection. Because the red is closer and at certain angles, the green and red are facing outwards, the image formed is much smaller, right? And the other thing is occlusion. This blue bit, it never shows up. To us, because we're looking at it from 3 dimensions, it's visible, but to the camera that's in the same plane as the image, it's being occluded by the rest of the object, right? So let's take away the intuitiveness and put the math in, right? Okay, let's start labeling points. The pinhole, where we have all the rays going through, we'll call it O, nice reference point. The point P is any point that we want to figure out where its image is. And its image is formed at P prime, right? From P, we'll drop a perpendicular to the principal axis and call it A. And similar to P prime, we find an image of this perpendicular point at A prime, right? So far, hopefully, nothing too weird. Okay, there's where it gets weird. So now we have 2 triangles. We have a triangle out here, outside the camera, and then we have a triangle inside the camera. And if you look at it, we have a perpendicular right angle triangle, and we have a pair of opposite angles at O. And this is enough to prove that the 2 triangles we have are similar, right? And I have some more math here. You can look at it if you want. If not, just take me on my word. The triangle out here and the triangle in here are similar to each other, and what that means is all of their angles are equal. So before we make it more complex, let's try and label more things, just so we have actual concrete values to stuff. So O, I already referred to it. It's a nice reference point, so let's call it the origin, right? And we have the origin, so we need to define the axes. By convention, we take the z-axis to be pointing towards the sensor, right? And x is arbitrarily chosen to be in the plane of the slide. So in this case, x is pointing up. Doesn't matter. It could have pointed down for all we care. So let's start labeling the stuff that we know. Point P, it's out in the world. And since the problem is to take the world and make it an image, we'll say that we know where point P is in relation to O. So we know the coordinates x and z. It's slightly odd. You're used to seeing x and y, but in this case, because of our choice of the z-axis, we call it x and z. A is trivially calculable because we just dropped a perpendicular, so we label it. P prime is labeled as lowercase x and z, and lowercase x is not known. A prime is labeled as 0, z, and it may not be intuitive to you, is that lowercase z is actually known to us by virtue of us building the camera. So we just take a tape measure, how far is the sensor from the lens or sensor from the pinhole, and we call that f. So just by construction, we know lowercase z is f, and the only unknown is this lowercase x, assuming we know all of these other things. So yeah, let's use the fact that we proved that the two triangles are similar to try and figure out what lowercase x is. So we take the fact that since these are right angle similar triangles, the ratio of perpendiculars is equal to the ratio of the bases. So A prime P prime, which is this length, divided by AP, which is this length, is equal to the ratio of A prime O, which is this length, divided by AO, which is this length. Again, this is simple geometry. If you do not remember this from high school, don't worry. We have links at the end if you want to deep dive or just get a refresher of all of this. So we write down all the things we know. So we get A prime P prime equals F divided by Z times X. And we do a little bit of moving around to figure out lowercase x is X by Z times F, right? All good so far. If you want to be slightly more specific, P prime is X by Z times f, which was lowercase x, comma f, because remember I said lowercase z is f. Because the sensor is one-dimensional, right, and we know that the image only ever gets formed at the sensor, we say that A prime is the origin of the sensor, right, because its x dimension was 0. So provided we can say that A prime is known at all times, we can just say P prime equals X, or P prime can be perfectly defined by X, right? So if all of that word soup doesn't mean anything, basically we can, instead of saying P prime is these two values, we can just say P prime is just the first value. So P prime can be fully defined by X by Z times F. So yeah, that's it for two-dimensional projection. We can do this for all points on the object and figure out where the image of every point in the real world will lie on the sensor. And now some of you may be wondering, hey, this is two-dimensional, I understand. What about the three-dimensional world? Turns out nothing changes. Genuinely nothing changes. It blew my mind when I realized that nothing changes. You just pretend the other axis doesn't exist. So now we have a two-dimensional sensor, so P prime has x and y, right? But you solve x like how we solved x just now. We solve y by basically removing x and replacing it with y. We just pretend the other axis doesn't exist, and it all works out. When you put it back together, everything works as usual. So x is what we figured out. Y, you replace the capital X with capital Y, and that's all the change that's needed, right? And this is nice, somewhat compact, but it's not quite the format we want it in, because if you've done graphics, sometimes you want to chain together translations and operations, and this is not the most conducive format to write stuff in. So let's complicate things, and hopefully make it easier at the end. But to complicate stuff, we'll introduce what's known as homogeneous coordinates, and the idea behind that is we want to have a representation where if we scale every element of the vector by some constant, we don't lose any information, right? This is not to say that they'll be equal after scaling. You just wouldn't have lost any information, and whatever information was already there can be calculated again, right? So we take a point P, which is two-dimensional, x and y, right? This could have been three-dimensional, four-dimensional, doesn't really matter. And we add an extra dimension to it, and we set it to 1, right? And we say this is the basis of homogeneous coordinates. Anytime you have a homogeneous coordinates in form of x, y, any number of dimensions here, followed by a 1, you can drop the final 1 and get back the original value, right? Now, if we multiply every element by some constant, doesn't matter, as long as it's scalar, we can multiply it by, let's say, k. We'll get a new vector. But because we had that 1 here, this final value will track the final scaling. So to go back, we'll say, hey, the final value is k, So we're going to divide everything by k. Every element gets divided by k, which gets us back to this form. And then we just drop the last dimension and get the original value, right? And if all of this seems arbitrary, it is. As far as I know, there's no like physical representation or understanding of why this is, right? But what it does is, much like imaginary numbers as compared to real numbers, just its existence and just adding this one extra dimension makes so many things possible in terms of what we can write as matrix multiplication or vector math. That would not otherwise be possible, right? So let's look at an example right now. So I said we wanted a simpler representation. So we had a p prime, which we had calculated before. And we want to come up with some constant c, in which case this could be a matrix or a vector, that operates on the input x, y, z, which is some point in the outside world, right? And if you look at it, this seems kind of not doable. If you're familiar with matrix math, at no point you learned that there was a division, right? You multiply and you add. Those are the two things that's possible. And this z as the denominator is really throwing a wrench in all the works, right? So either you make c a function of the input, or you don't have a constant c, right? OK, so how does homogeneous coordinates help us? Let's try and make p prime homogeneous. Let's add this extra dimension 1. And because the z is what I said was giving us trouble, let's multiply everything by z. And remember, because of how we define homogeneous coordinates, nothing is really lost here, right? It's just a new representation of the same information. So we now have this new value. And we want to write this new value as c times xyz. And this is surprisingly trivial. We've just scaled x and y by f, and that's it. So C can be written as an identity matrix that has its first two elements replaced with F, right? So all this fancy math that we have here, all of this can be represented with a simple matrix multiplication. The only crux being P prime is in homogeneous coordinates. So the value you get out might need to be tweaked before you can actually display it or act on it. Or sometimes you don't, right? So yeah, that's how projection works in a pinhole camera model, right? One simple scaling operation, as long as you remember you're in homogeneous coordinates and don't accidentally use it directly. But again, pinhole cameras aren't really a thing anymore, as far as I know. If you look up Google, try and find images of pinhole cameras, you'll get maybe 3, and then about 100 diagrams of a pinhole camera model, right? So now that if you have lenses, which is most cameras, what changes? There are a few things that change, two of which we can account for within our pinhole camera model. But then we have something we call lens distortion or aberration. Distortion is something, both distortion and aberration happen because of manufacturing defects, material properties, and stuff like that, and really can't be perfectly represented by any mathematical model, right? There are certain models, Android uses Brown-Conradi model, that mix up a few other models and then give you a final picture. So what we do is, we're not the camera makers, so we say, hey, someone else made the cameras, it's their problem. You tell us what the distortion looks like, and we'll account for it at the end, right? And the other two we can handle within our pinhole camera model. So let's take a look at those real quick. So the two things are optical axis translation. Oh, it's called optical axis now from principal axis because we have a lens, so optics. It's the same idea. It's just a line passing through the center of the lens. And because you have things like OIS, or the lens might naturally move, or the sensor might move, this axis can move around relative to the lens. So what used to be at A prime, 0, z, might have moved to A prime, which is now Cx, some arbitrary value, it doesn't matter what. Remember, Z is still the same. Whoops. Z is still the same, so F remains the same. The only thing that's changed is 0 versus Cx. If you can imagine what the image comes in, nothing really changes in our math, in the whole thing we ran through, all of this intuitive way we went through. Nothing here changes, right? All that changes is the final coordinates we get is just translated by the value of Cx. And So all we do is we run the math exactly as is, and at the end, when we have the image, we say, hey, shifted by this value that we know the optical axis was shifted by, and that's it. Sensor skew is slightly less difficult to imagine, slightly more difficult to imagine, my bad. If you've ever looked at a magnifying glass at an angle, it kind of looks weirdly tilted, right? And turns out the mathematical operation for that is called shearing. It's a ratio of how far you're away from the center to the displacement at that particular point. Crucially, what I want to point out here is that this happens before the image is formed. So putting everything together, we get something like this. And anytime you see a bunch of matrices multiplied by a three-dimensional point or any dimensional point, think of it as the operations going right to left. So we take a three-dimensional point, right, which is in our real world. We skew it to account for any time the plane of the lens is not parallel with the plane of the sensor. Then we project it to get the image of the skewed point, and then we translate it to compensate for in case the optical center had moved around or the optical axis had moved around, right? But remember when I said you have to go right to left? That only works when you want to understand how these operations are applied. You can totally just multiply these three things together and do the whole thing as one single operation. So that is what we do. We multiply these three things together, and we come up with what's known as camera intrinsics. So this is one operation, camera intrinsics times input being somewhere out in the world, to get its image. Again, this is in homogeneous coordinates, so not exactly the image we get. If you're doing graphics, if you're doing AR, right, you may have points that you've already worked on. You may have done some transformations to it. And what ends up happening is the input you get, the three-dimensional point you get, is often in homogeneous coordinates. So we need a homogeneous version of camera intrinsics, which is actually pretty simple. We add one, we don't add one, we get one. We get an additional dimension here, and we simply cancel it out by adding a column of zeros. So this finally is the picture for for a camera looking at the world and creating an image as one mathematical operation, right? Do this for every point in the world, and you'll figure out what the camera creates as the image. But that's only half the story. The other half is, can we go back? Can we take an image? And can we figure out where the point is in the 3D world, right? Is that even possible? And for that, I'd like Chen to take over.
Thank you, Avi. So Avi talked about how we can go from a point in 3D space with respect to the camera, and how we can project the point back into the sensor. What I'll be talking about is, first of all, whether it's even possible to go back from the camera sensor to 3D space, and if that is possible, what we can do with that. So let's start off. So before we can figure out whether it's possible to do that or not, let's go over some more concepts, especially regarding the fact that we saw when you have a point with respect to the camera's coordinate system in 3D, how do you go from there to the sensor? But in practice, lots of times we don't have the coordinates of a point with respect to the camera's coordinate system. We might have the coordinates of a point with respect to a third, or like the world coordinate system. So for example, if I'm standing here and I want to find out the coordinates of the light there, and I have a smartphone, I may not know the coordinates of that light with respect to the smartphone, but I may know it with respect to, let's say, that projector, which might be the world coordinate frame. So can I go back from that world coordinate frame to the camera sensor? So I've removed the 2D diagram which we had for the Google logo, and I'm just concentrating on one point. And we have a laser pointer here. So let's consider this is one point in the world coordinate system. And with respect to the world coordinate frame, the vector to that point is called RW. And then you have a ray of light, which again, like Avi mentioned, let's assume we have a pinhole camera here for simplicity. It goes from the world point and it's projected onto the camera sensor and produces a vector Ri, which like stands for the image. So our job here is to see if we can go from this point to this projection and what's the mathematics behind it. So what Avi mentioned was the transform here that we have, xc, yc, zc, which is the point from the camera coordinate system's point of view, and how you can go from here to xi, yi, which is basically the point on the sensor coordinate system. But what we want to do is we want to go from xw, yw, zw, which is the coordinate in the world coordinate system, directly to xi, yi. How do we do that? Now, if we think about it, if we figure out the transformation which goes from xw, yw, zw to xc, yc, zc, then we pretty much got it, right? Because we already know the transformation from xc, yc, zc, which is basically the 3D point in the camera coordinate system, to the sensor coordinate, sensor 2D image coordinate. And naturally, the transform which makes the world coordinate which makes the point go from world coordinates to camera coordinates does not only depend on the camera parameters. It depends on where your camera is in the world itself. So if we look at let's try to write some vector equations. A simple vector equation is if you have your world point and are represented by RW, and if I have the same point, we look at it from the point of the camera coordinate frame, let's call it RC. Then RC is equal to RW minus CW. Minus CW because for vector addition you need to invert this vector, which is represented by green. And then you can add this. One thing to note though is that this equation is only valid when all of your vectors are represented in the same coordinate system. So it's either in the world coordinate system or the camera coordinate system. If there's separate coordinate systems, this equation is not valid. You might be able to modify it for it to be valid, but in itself, it's not valid. So like I mentioned, we want RC in terms of the camera coordinate system. At the same time, we do know RW and CW in terms of the world's coordinate system. But as I mentioned, we need to write this equation with respect to the same coordinate system, but we have two different here. So what do we do to make that possible? So Avi mentioned that if you know computer graphics, you already know most of this talk. So this is a simple computer graphics problem. It's a problem of translating between two coordinate frames. So we've already taken the translation into account here, which is CW. So what we need to do is we need to take potential rotation into account. It's possible that the world coordinate frames orthonormal basis vectors, xw, yw, zw, may not be exactly aligned with what the camera coordinate frame is. So how we handle that is we use a transformation matrix. In this case, the transformation matrix would be a 3x3 matrix. If you had 2D, it would be a 2x2 matrix. But since we're in 3D, it'll be a 3x3 matrix. One thing to note though here is that the rows of this matrix, they're going to be orthonormal to each other. So that means if you do a dot product of any two pairs of the rows in this matrix, it'll come out to be 0. This is something which seems insignificant right now, but we'll use it later in the talk. So now that we've got this rotation matrix, we're able to write this equation without worrying about the fact that RW, CW, and RC, they're defined in different coordinate systems because of the fact that now we've taken into account this rotation matrix, and this equation is now valid. So if we expand this equation, what does it become to? So it comes out to RC is equal to rotation matrix multiplied by RW minus rotation matrix multiplied by CW. So that R multiplied by CW, that can be, let's count it as translation because that's what it's really doing. It's looking at how far the camera coordinate system is with respect to the world coordinate system. Now, if you think about what Avi mentioned in the slides for camera intrinsics, this operation it's a combination of matrix multiplication as well as addition. Now that's kind of undesirable because when we're doing some graphical computations, we ideally want only matrix multiplication. because then you can do things like you can chain operations, you can chain skew, rotation, and various things. If you have an addition, that makes things harder. So you might be thinking, how do we now actually convert this into just one matrix operation? And the answer again is homogeneous coordinates comes to our rescue. If we add one dimension to the rotation, the combined rotation and translation matrix, we can, with one matrix multiplication, represent the equation that I'd mentioned before, this one. So with one matrix multiplication, you can go from xw, yw, zw to xc, yc, zc in homogeneous coordinates. So cool. Now we can go from xw, yw, zw to xc, yc, zc. And once we have that, we can just use camera intrinsics to go back to xi, yi, t, which is the scale of the homogeneous coordinates. So if we just expand the equation, taking into account intrinsic parameters, this is the equation that we have. It's basically, you go from right to left. You start off with the world coordinates, x, w, y, w, z, w. Then what you do is you take into account the extrinsic parameters. Once you've gone there, you have xc, yc, zc. Then you multiply the intrinsic parameters. Once you have them, you have your final sensor coordinates, xi, yi, and t, which is the scale for the homogeneous coordinates. So if we combine the intrinsic and extrinsic parameters, we basically just do a matrix multiplication. We get something which is called the projection matrix. So all that's doing is it's basically just combining those two matrices into one. And with one equation, you can go from your world coordinates to what you have on the sensor coordinates. Okay, so now we know how to go from world coordinates to sensor coordinates, but now you might be thinking, how do we actually get the projection matrix? Like if I have a camera, I don't know what the projection matrix is. How do I actually get that? So that is something which we call camera calibration. That's the process of estimating the projection matrix. So you might be thinking, how do we actually do it? So let's say the situation here is that I have a camera and I have the world around me, and maybe I have access to a few objects. How am I able to estimate what the projection matrix is, which is basically the mapping from the world to the camera? We can use the fact that if we know the exact point in space of something in space, and we also know the corresponding point in the image, we have an equation, the matrix equation, which was there in the last slide, representing the whole mapping. And if we have this mapping for multiple points, we can kind of solve for the unknowns. So to make things more concrete, let's take an example. So let's say I have a cube in front of me, which is of known geometry. So I'm assuming that my world coordinate starts at the bottom right edge of the cube, and I know exactly how high the cube is and where it's placed with respect to the world coordinate frame. Now what I do is I take an image of this cube, and I also know where exactly things like, if you see these points, like the purple point here, or the blue point here, or the green point on the top edge, I know where exactly these points are with respect to my origin, which is the bottom right edge of the cube. Now, if I take an image of this and try to find the corresponding points in the image, then I have an exact one-to-one correspondence between the world coordinates and the coordinates on the image. And then I can basically solve some equations for the projection matrix. So what it looks like is this. Let's say I took an image of the cube. I have one equation, and let's say that this image is called the jth image. So let's say we take n number of images, and this is the jth image. And the jth image is basically, I should correct myself, it's not the jth image. We're taking one image, but we have n number of points. The jth point is the one which is the blue one here, so which is like roughly on the center of the cube on the edge. I know where exactly this is in the world, and I know where exactly this appears on my image. Now I have an equation which maps the coordinate of this point from the world to the image. If I have one such matrix equation, I have two such linear equations, because there's one for x and one for y. And now you can kind of guess. We have 12 unknowns. If we have 6 such points, we have 2 equations per matrix, so 12 unknowns and 12 equations. So we're basically able to solve for all the unknowns in the projection matrix. So that's how you get your projection matrix. Now the question is, if we have a projection matrix, are we able to compute the intrinsic and extrinsic parameters of the camera system? So for that, let's step back a little bit and look at the properties of the intrinsic and extrinsic parameters. For your extrinsic matrix, we see that the rotation matrix here, I mentioned that the rows here are orthonormal to each other. So that basically means that if you take a dot product of any of the 2 rows in this 3x3 submatrix, the answer is going to come out to be 0. So that's one fact. The other fact is that the intrinsic matrix here, it's an upper right triangle matrix. So that means that anything that's below the diagonal is 0. So taking these 2 facts into account, it turns out that we can actually decompose the projection matrix that we found out a couple of slides back exactly into its intrinsic matrix as well as the extrinsic matrix. Now, how exactly that is done it's a little convoluted and we're limited on time, so I'm not going to go into the details, but it's a process called QR decomposition, and I have a link here if you'd like to see the details. So from the larger picture, we just from one image of a well-known object, and we have one camera, we're able to actually know the exact mapping from the world to something on the sensor. So that's what we figured out till now. Now let's see how we can use these facts. Like, can we use it for some applications? So the first one is, let's say we'd like to estimate the depth of a point in the world just using a camera. So like the scenario here is you've got one single image. You got one image of a point in space, and you also have a camera with known intrinsic parameters, and we can know that using the process that we followed in the previous slides. Now the question is, can you know the corresponding 3D coordinates for that particular point on the sensor? So if I look at, just to repeat myself, I have a point on the image, xi, yi. Can I know where exactly this point would lie in real space, in 3D space? If we go back to the pinhole model, how does projection really work? Let's say I just have any generic point x, y, z. Any point on this line is going to project to the same point on the sensor. So the answer is, just with one image, it's impossible to tell where this point actually lies in space, because it could be anywhere here and would still project onto the same point on the sensor. So can we do something better? Is there some other way of knowing? Can we like maybe augment the information that we have to still know the exact point that this point on the sensor corresponds to? So it turns out that what we could do is we could shift our camera a little bit by, let's say, a horizontal distance d. And I'm saying horizontal here just for simplicity. You could also move it vertically or in some other direction, but it just makes the math simpler here if we move it horizontally. Then what would happen is, you know that you have 2 projection points, and these 2 projection points are from the same point in space. So what you do is, you draw 2 rays back from the sensor to the supposed point, which is unknown that we need to find. And where they meet is the actual point corresponding to these 2 points on the sensor. So now it's basically just simple coordinate geometry. If you know the intrinsic parameters, it's pretty easy to find x, y, z. And z is basically the depth here, and that's d multiplied by fx over something that we call the disparity, which is basically the difference in the x coordinates of the 2 corresponding points on the sensor. And like I said, it does not necessarily need to be horizontally displaced. If it was vertically displaced, you can do the same thing as well. So cool. Now we figured out how to find the depth and also the x and y coordinates using 2 different images of the same point, assuming you know the camera intrinsics and it's the same camera that you're using. So let's put it together to create a simple AR effect. Let's assume that I want to place a small Android figurine somewhere near this Google sign that I have in space. So how would I go about doing that? What I would do is I would first I'd first want to know where to put the Android figurine in space. So for that, I want to know where exactly the Google sign is in space, right? And how do we do that? We do that similar to what I mentioned in the previous slide by using stereo vision. I use 2 images of the Google sign from slightly different points of view. And using triangulation, I'm able to find the exact X, Y, Z coordinates of, let's say, this particular point on the Google sign. And I can do the same for the others. Now, let's say I figured that out. I want to now place my Android figurine somewhere near the Google sign. So let's say maybe in between the topmost red point and the bottommost green point. So I know that. Now what I do is I place a virtual Android there, and then I project back. So I project back onto the camera sensor the Google sign as well as the Android figurine, taking into account occlusion. And by occlusion, I just mean that it's possible that your Android figurine might cover up some parts of the Google sign. This is something similar to what Avi mentioned in the first couple of slides when he was explaining the pinhole camera. And yeah, that's basically the process. It's a simple way of creating an AR effect, and it'll make it realistic because of the fact that we're actually using camera projection. So we looked at a couple of ways on how we can use the intrinsics and extrinsic parameters of a camera system, and how we can use it to estimate depth and also create a simple AR effect. Now, Kailiang will walk you through how we can actually use these things for some more complicated use cases, such as 3D reconstruction. And also, since we're here for an Android developer's talk, he'll touch upon how through the Android Camera 2 API, you can actually use all these properties and what you can do with them.
Thanks, Jayant. I think that we go through the round trip from 3D to 2D and 2D to 3D. Everything that in summarize can be at a point, and if you define the origin and the one coordinate system can be vector, and then I use the matrix as the homogeneous transformation that to convert one coordinate to another coordinate. So I will briefly talk about another application that will be more advanced usage. I will make more dense math here, but just briefly talk about the keywords and what's the key technology here. So we know the structure from motion is to reconstruct the camera poses in the 3D structure of the scene in the world, and back to the project back to the as the 2D images. Like you see the light, you know the structure. Because our eyes is like the lens, basically projected, you know the depth of each point on the real world. So that's how the back projected. If you get the 2D images and get all the points to the series of images, you can back project it to know the structure of this scene and also how distant from your cameras. So basically like this, so you get a series of pictures, 2Ds, and you can back project it to get a reconstructed 3D scenes in the real world. So I will briefly talk about it, maybe faster to go through the pipeline. So basically you have a series of 2D images captured from different angles, or we call them multiple like viewpoints. And then you get a camera calibrated parameters, so you can undistort it, this image based on lens distortion coefficients. And then you need to detect the key feature points, which is more resilient or robust to the scale and the rotation, because sometimes we get a series of 2D pictures, but some of the resized and some of like have illuminance changes based on the different camera settings. And also you basically want to get it robust to the scale, rotation, and illuminance changes. So that'll be this algorithm more robust to extract all the key points from different images. And then normally we use the sift or surf, and then I'll put a link here. When you get a material, you can deep dive into it. And then we want to match these feature points on different images or image planes to get a correspondence between them. So basically here we can use the template matching. And you imagine you get a small picture of your face, and you want to slide your face on this big picture of your party or family picture. Find a similar pattern. This is called a template matching. Try to use in the cross relation between the small images patterns on top of the bigger images. Then after you build this correspondence, then you really wanted to reconstruct, back projected your 2D points back to the real world to get this, how this location of the 3D points should be, and how your camera poses based on the rotation and translation in the 3D world. And here on the right, the diagram shows called epipolar geometry to explain there are some constraint or describing the relation between different cameras and their poses, and based on the images and their in a 3D world, how the relation be. And here is based on some metrics in a homogeneous transformation. Basically, the problem here you want to solve is you want to estimate which called essential metrics, try to estimate the camera poses on each angle, and then you get these 2 points on each image planes and back project to the 3D world. So there's some classic problems here. I would omit the mess. Basically, it's like you at least need 8 points of each image to better estimate the camera poses and reconstruct the 3 points in the world. So here they simulated the 3D points. Like after you get the camera pose estimation, you try to triangulate it. It means to estimate the 3D location of each point based on you have the camera intrinsics, extrinsics, and also the 2D points on each image. So basically you reconstruct all the points, and using the boundary adjustment, it relatively optimized to filter out which is the bad 3D points, which is based on the reprojection errors, which is cost function. So after that, you will get a set of the 3D points, which we call point clouds. Then you can do the texturing or rendering, and then get a 3D structure from the scenes in the real world. So here, there's a classic problem called perspective with endpoints. It can be n, it can be 3 or 2, based on the information you have. If your camera is already collaborated beforehand, you would the perspective is like 3 points or 2 points. Here's the classic algorithm used to the ransack that to iteratively optimized based on the points you projected and also the reprojection errors. So that's all the math that we have. Let's back to the real world. I will introduce some of the basic Android APIs that help us to build the advanced applications based on all these concepts. So basically, we have these 3D coordinates. It's a quick recap from the 3D real world and project the transformation to the 3D camera coordinates and down to the 2D sensor or image plane coordinates. And from the 3D to 3D, it's a rigid transformation, which will preserve the shape and the sizes of the shapes of the scenes. And then from 3D to 2D, it's a perspective transformation. Basically, you have, you see a different scenes based on different angles or in a perspective way. That's how the perspective transformation, or you can understand it as a homogeneous transformation. So the camera 2 APIs provide us, which calls a lens intrinsic calibration. Basically, you can get 5 parameters, which is mapping to the intrinsic parameters according to Avichal and Jayant mentioned, the pinhole cameras. And then you can get extrinsics based on camera 2 APIs, which have 3 APIs lens pose reference, which you can understand and define the origin of the world coordinates. Because every point of vector, it defines a vector, you need to understand which the origin of the world, what's the reference. So here the possible values can be primary camera, or the camera center, or it's a gyroscope on your device, or can be the automotive sensor, which is the Android Auto sensor. Here, undefined is being used like in some of the use case like a foldable device. When the fold, because based on the design and topology of each foldable device, it's hard to define its which reference or the lens pose rotation and translation based on. So maybe you need a hinge position sensor to help you to get a better understand or accurate pose rotation and translation. So based on the reference, you get the rotation and the translation. So basically, you get all the metric coefficients here. Maybe you need to do the continuum to the rotation metrics based on mapping equation, but the API documentation mentions that you can get all the extrinsic metrics. So then the lens distortion. So the lens distortion basically it's using the called the Brown-Conradi model. They have the consists of the radial lens distortion and the tangential distortion. Normally we have normally faced like a radial distortion that is the bending around the the edges compared with the center. So like the fish eyes lens, and sometimes you need to undistorted images. So this API provides the coefficients covering these two distortions. So based on that, you can undistorted images for better matching. Then some advanced information you might need beside the camera is the sensor APIs. So based on the IMU, inertial measurement unit, two typical classical examples, accelerometer, so you can get the information when the devices move along the three axes in a linear acceleration. And a gyroscope, you can angular velocity based on the device, the roll, pitch, and yaw. So combine these two and the camera information, basically, what we can do based on this information. So the basic problem we want to solve is, okay, where's my camera device or your mobile device? And where did the real objects referring to your camera device in the 3D world? And if you want to augment or put a virtual object into the 3D world, how do it look like? These three problems can be solved based on the camera parameters and the sensor parameters. So more advanced applications I listed here is like depth estimation, motion tracking, and like visual simultaneous localization mapping, which is normally used in the robotics and the self-driving cars. So just take away, like today we briefly talk about pinhole cameras, homogeneous coordinates, and we talk about camera intrinsic parameters, extrinsic, and lens distortion coefficients. And then we briefly talk about the camera APIs and applications. So really want to try that and give us feedback. And if you want to have a further discussion, you can join our developer community here. So that's for further study. And I'm sorry the presentation is not available on the GitHub, but we will upload it in 2 or 3 days. You can get all the links and the materials. So thank you for your time today.